So we have seen that the angular momentum can be orbital angular momentum, or it can also be spin angular momentum. The orbital angular momentum is characterized by quantum numbers L and ml, such that L can have values from 0, 1, 2, etc. And ml can have values from minus L, minus L plus 1, etc. 0 up to plus L. So there can be 2L plus 1 values for this ml quantum number. Now, by analogy with the orbital angular momentum of a particle, the spin angular momentum is also characterized by two quantum numbers: the spin quantum number S and its projection to z-axis, or along the direction of a magnetic field, which we represent by ms. The projection of the spin angular momentum along a field direction or along the z-axis is represented by the quantum number ms. So these ms can also have values from minus s plus 1, etc. up to plus s. So there are 2s plus 1 values that can have for this quantum number ms. Now, since the spin has only two components for electrons, you can write this 2s plus 1 equal to 2. That means the quantum number for electron are s is equal to half and ms is equal to plus or minus half. And these are the two quantum numbers for the case of an electron. It can have a spin quantum number half and only two possible orientations with plus half or minus half. Now we are trying to develop a general theory for the spin in analogy with the general theory of angular momentum that we have derived in the beginning of this module. So the spin angular momentum is represented by the operator S, and its components are given by Sx, Sy and Sz, similar to the components Jx, Jy, Jz, or for the orbital angular momentum Lx, Ly and Lz. Now they are defined in a way similar to the way we define the general angular momentum. So this spin angular momentum is defined by the commutation relations. The commutation Sx xy is given by IH cross Sz, and commutation Sy Sz is given by IH cross Sx, and commutation Sz Sx is equal to IH cross Sy. So this is the definition of the spin angular momentum. This is exactly similar to the definitions that we have given for the general angular momentum or the orbital angular momentum. Now since square and Sz commute, we can have a common eigenstate. So if you take the commutation relation between S square and Sz, or any component of this spin angular momentum, it will be 0. So these commuting operators tells us that they can have a common eigenvector. So we can write the eigenvalue equation for S square and Sz as S square, we take this common eigenstate as S ms. This is equal to h cross square into S into S plus 1 S ms, and for Sz it is given by H cross ms s ms. So this is identical to the eigenvalue equation with the general angular momentum vector j. So there we use the quantum numbers j and m. Here we use, instead of j we use s, and instead of m we use the ms quantum number here. So ms can have values from plus s to minus s. Similarly, we can write with the raising and lowering operators, we can define two operators, s plus or s minus, in a similar fashion that we did for the general angular momentum case. So this is given by h cross into square root of s into s plus 1 minus ms into ms plus or minus 1 s ms plus or minus 1, where this s plus or minus is defined in terms of sx and sy. So this is given by sx plus or minus isy. Okay. And you can also show that the commutation of the expectation sx square is equal to the expectation xy square, and this is equal to half of the expectation of this x square minus s z square. So this can be written as h cross square by 2 s into s plus 1 minus ms square. So you can easily identify these kind of expressions if you clearly understood the general angular momentum theory. So those who have confusion to identify, or how if you don't know how to get these terms, you are advised to look into the general angular momentum theory. So there we have similar kind of expressions. The only variation is, instead of general angular momentum, we have taken the spin angular momentum. Okay. Now the spin states form an orthonormal and complete set of bases. That means we can write s prime m s prime s m s is equal to delta s prime s delta m s prime m s, and the completeness condition tells us that summation of ms, it can have values from minus s to plus s, then s m s s m s equal to the unit matrix or the identity matrix. Okay. Now for a particle with a spin half, the quantum number, we have seen that the quantum number ms can take values, only two values. So what are those possible values? Ms can have values minus half or plus half for a particle with a spin half. Okay, so such a particle can be found in the state as ms. So what are these possible states such a particle can be found? These are the states of minus half and plus half. So a spin half particle can be found in either of these two states. Okay. So the eigenvalue equation for spin half particles can be written as, you can write S square for a spin half particle. This is half, and ms can have value plus or minus half, and this is given by h cross square into half plus 1, that is s into s plus 1. Then we have half plus or minus half state. So this can values 3 by 4 h cross square half plus or minus half. Similarly, for the z component of the spin angular momentum, we can write sz half plus or minus half is given by plus or minus half h cross half plus or minus half. So this expression tells you that the spin may be represented graphically by a vector of length given by root 3 by 2 h cross. So the endpoints of this vector lies on a circle of radius given by root 3 by 2 h cross. So the spin can be graphically represented in this way. If you take this as the arbitrary z direction, and let's take this as our x and y components, sx and xy components. So spin for a spin half particle can be represented by a vector like this, and its magnitude is given by root 3 by 2 h cross. And we have seen that or we can identify, or we can imagine it as rotating along the surface of a cone. So this one is actually a part of a cone. So this spin vector can be anywhere on the surface of this cone. So this has equal probability of being found anywhere on the surface of this cone. So its projection onto this direction is given by the value of sz. So this is half h cross. Similarly, there is another possible orientation which is given by minus half h cross. So these two are the only possible orientation for a spin half particles, and you can easily find out this half angle theta for this cone. So this angle theta is given by cos inverse the value of ms divided by square root of s into s plus 1. And for spin half particle, this will be, if you substitute the value for s equal to half and ms either plus half or minus half, you will get this is cos inverse of 1 by root 3. So this angle will be 54.73 degree. So this is the graphical representation of the spin angular momentum. The projection of the spin on the z axis is restricted by these two values, plus or minus h cross by 2. So these, if the projection is having a value plus h cross by 2, we say that this is a spin up state, and if the projection is having a value minus h cross by 2, we say conventionally it as a spin down state. Now if we try to represent this matrix form of a spin half particle, we can easily see that the operators s square and s are diagonal in this basis, yes, ms basis. So if you consider this basis, these two operators are diagonal. So the matrix elements for s square and s can be easily found. You can write for s square operator The matrix elements are given by S, Ms, and here you can write S prime, Ms prime. So this is given by, so eigenvalue equation tells you that this is H cross square into S into S plus S plus 1. Then we have seen the orthonormality condition that tells us delta S prime S and delta Ms prime Ms. Similarly, for the Z component of the spin, we can write the corresponding expression for the matrix elements S Ms so this is given by H cross Ms delta S prime S delta Ms prime Ms. So the S square matrix for a spin half particle can be written as, so if you remember the way we have done it for the general angular momentum, we can take S along this direction, then Ms along here, S prime in the downward direction, Ms prime also in the downward direction. And for spin half particles, S is always half, and Ms can have values from half or minus half, only integer, only plus half or minus half values. So here also we have half, half, minus half. So we can see that only we will be having non-zero diagonal elements for these matrices, and its magnitudes are given by this expression H cross square S into S plus half. So if you put S is equal to half, that will give you 3H cross square by 4. So this will be 3H cross square by 4. Then the matrix elements are 1, 0, 0, 1. Similarly, for the SZ matrix, you can write it as its value is given by MSH cross. So this is given by H cross by 2. Then you can have values 1, 0 and 0, minus 1. Okay. The matrices for S plus and S minus can be obtained from an expression similar to one that we have seen for the general theory of angular momentum. So you can see that for example, for X plus or S minus is S Ms, the matrix elements are given by S prime Ms prime. This is equal to H cross into square root of S into S plus 1 minus Ms into Ms plus or minus 1. Then we have delta S prime S, then delta Ms prime Ms plus or minus 1, right? Because depending on whether it's a raising or lowering operator, you will get a state plus 1 or minus 1. Okay, so you can do it yourself. So what you get the matrix elements for this S plus, for example, is what you have to do is just substitute the values for S and Ms, and for S plus operator you can write it as H cross 0, 1, 0, 0. And for S minus, this is given by H cross 0, 0, 1, 0. So once you know the matrix elements of X plus and S minus, you can construct the matrix elements for Sx and Sy, because Sx is given by half of S plus plus S minus, and Sy is given by 1 by 2i of S plus minus S minus, right? So if you take the sum of S plus and S minus, you can write the matrix element Sx is given by H cross by 2, 0, 1, 1, 0. And the matrix elements for Sy is given by H cross by 2, 0, minus I, 0. So this is the sum of Sx and S minus, and this is the difference between Sx and S minus matrices. So you can see that when we have a particle with a spin quantum number equal to half, we have seen the matrices, the all components for Sx, Sy, Sz and S square. Now Pauli introduced some matrices to conveniently represent these kind of spin components. So he said that, or he has shown that spin vectors can be related to some matrices called the Pauli spin matrices by this relation. The spin angular momentum is equal to H cross by 2 sigma. So this sigma is called the Pauli spin matrices. Pauli spin matrices. So what are these matrices? It has three components: sigma x. Sigma x is given by these terms. Sigma x is given by these matrices. So what you have here is 0, 1, 1, 0. Okay. And sigma y is given by this matrix. So this is given by 0, minus I, 0. And sigma z is given by this one, 1, 0, 0, minus 1. So this will be 1, 0, 0, minus 1. So these are the Pauli spin matrices. So using Pauli spin matrices, we can conveniently represent the spin vector, or the spin vector can be connected to the Pauli spin matrices by this relation. So Pauli spin matrices satisfy certain properties. So let's see what are those properties of these Pauli spin matrices. You can see that the square of any of these spin matrices, for example sigma x square or sigma y square or sigma z square, this will give you the identity matrix. You can verify it yourself. Take the square of any one of these matrices, you will get an identity matrix, terms involving only 1. So you can write it in general that this sigma j square is equal to I, where j stands for x, y or z. Another property is that they are anti-commutating. So that means if you take the product between sigma x, sigma y, then plus sigma y, sigma x, this will be 0. Similarly, you can say that sigma y, sigma z plus sigma z sigma y is equal to 0, or sigma z sigma x plus sigma x sigma z is equal to 0. They are anti-commuting. Pauli spin matrices are anti-commuting. So in general you can write it in general form as sigma j sigma k plus sigma k sigma j equal to 0 for j not equal to k. Now another property of Pauli spin matrices is that they have some kind of commutation relation like this: sigma j sigma k. The commutation between any components of the Pauli spin matrices are given by 2i epsilon jkl sigma l, right, where this epsilon jkl is an antisymmetric tensor which is known as Levi-Civita tensor. Levi-Civita tensor. It has values. This sigma j kl can have values plus 1 if j kl is an even permutation of x, y, z, and this is equal to minus 1 if jkl is an odd permutation of x, y, z, or this is equal to 0 if any two indices are equal. If any two indices are equal. So that is the values of this Levi-Civita tensor. Now you can also see that these Pauli matrices are Hermitian matrices. They are traceless and they have determinants equal to minus 1. What are its other properties? They are Hermitian matrices and they are traceless matrices, and they have a determinant equal to minus 1. That means we can write sigma j dagger equal to sigma j, since they are Hermitian, or you can write the trace of any of these Pauli spin matrices equal to 0. You can write the determinant of any of these matrices are minus 1, where j stands for x, y, or z. So let's consider this commutation relation once again between sigma j, any two components of these Pauli spin matrices, sigma j and sigma k, and this is given by 2i epsilon jkl sigma l, right? So let's say j is equal let's take j is equal to x and k is equal to y. Then we can write sigma x sigma y, the commutation sigma x sigma y, that is in principle sigma x sigma y minus sigma y sigma x. So this is equal to, on right hand side we have 2i, then we have a value of 1 for the even permutation of x, y, z. So if you take this is sigma z, then this one has a value 1. So we have 2i sigma z on right hand side. But we have also seen that they are anti-commuting. That means this sigma y sigma x is negative of sigma x sigma y. Since they are anti-commuting, this is negative of sigma x sigma y. So the left hand side can be written as 2 times sigma x sigma y, and on right hand side we have 2i sigma z, or you will get another relation: sigma x sigma y is equal to I sigma z. Now if you multiply with sigma z on both sides of this expression, you will get sigma x, sigma y, sigma z is equal to I sigma z square. But we have seen that Pauli spin matrices has a property, the square of these matrices are 1. So this is identity matrix. So you can write this as sigma x, sigma y, sigma z is equal to I into the identity matrix. Now since the spin does not depend on the spatial degrees of freedom, the components of the Sx, Xy, Xz of the spin operator usually commutes with all the spatial operators. For example, it commutes with the orbital angular momentum L, or it commutes with the position vector, or it commutes with the momentum operator. All these are spatial operators. So you can write the commutation between Sj and Lk is equal to 0, or the commutation between Sj Rk is equal to 0, or you can write the commutation between Sj Pk is equal to 0, where this j and k can have values like x, y and z. So it commutes with the orbital angular momentum, it commutes with the position operator, it commutes with the momentum operator, or spin in general commutes with all kinds of the spatial operators. Okay.